Okay, thank you so much for the invitation again, Professor. So, hello everyone. Today, I'd like to introduce a joint work with my supervisor, Professor Parilina. And in this work, we mainly explore the stability of partition structures when players are engaged in network structure. So there are two structures in our work, and I will introduce them in details later. As we know, in many contexts, players are heterogeneous. So players can be divided into different types by their gender, ages, cultures, or like native languages. So there are many works working on games with collation structures, and in many works they call partition structures. And like Ullman and Dries in 1974, they investigate the cooperative games with collation structures. So before cooperative games is studied just for the grand collation. In that work, people form the collation, and the cooperation is accomplished in any subset of the grand collation. And then because in that work, the utility of each player is only determined by the members inside the collation, but not related with the members outside the collation. So it is a kind of game called hedonic games. And of course, there are many works working on collation structures, which is non-hedonic games. Like in 1997, he studied two-stage games of collation structures. At the first stage, people form the collation structure, and at the second stage, players gave the strategies to get the utility. And in that work, because the author studied the externality of the collation structure, it means that the formation of the collation or the merger of the several collations have some positive or negative for the the outside members. So it is not hedonic games, but non-hedonic games. And also there are some works working on the dynamic process of the collation formation, like Professor Parilina and Selagov. They just model the transition of the between collations as a Markov process, and they study the existence of the stable collation structures. And like in our works, there are some works just combine the network structures and the collation structures, like several works of me and Professor Parilina. We study the pairwise stability of networks when players are partitioned into different collation structures. And because players are heterogeneous in the collation structure, so some works working on homophily and the patterns of segregation of players and or network structures in some work. Like DeMartin and Zenon in 2017, they just divide the players into two communities, and players inside one community, they pay very low cost for the link maintenance, and to pay a higher cost across the communities. And they study the stability of networks under three cases, like high intra-community cost, medium in community cost, or very low such cross cost. And they find very obvious segregation in the stability of like network structures. Now let me introduce our work. Here we partition the set of players into the finite set of groups. And here pi I is just the label of the group player I belongs to. For instance, if player I belongs to the group N2, and 2 is just pi I. And we also put players into the network structure. So this is the second structure of our work. And for each player, we focus on the neighborhood composition of each player. So here we define the set of neighbors of player I who belong to the group NK. So NIKG just is the set of neighbors of player I who belong to the set or the group NK. And with the partition structure and the network structure, we can see three examples here. Very symmetric and simple regular network structure. The first is a star network, and there are 6 players, and there are 3 groups. Player 1, the central player, and the player 4, they are in group. They are in one group. And player 3 and player 5, they are in one group. And player 2 and player 6, they are in the other group. And for this complete network, there are also 8 players and 3 groups. And for this balanced and complete bipartite network, there are 8 players, but there are only 2 groups. With the 2 structures, we define the utility of each player I as the difference between 2 terms. The first term is the benefit term. It is one of the most used benefit function in the network games. So as we see from this function, the benefit that the player I get from player G is only determined by the distance of the 2 players. And the second term is the cost that the player I need to pay to maintain his direct connections with all his neighbors from various groups. And here we propose 2 types of cost functions. Under the first cost function, if players I and G, they belong to the same group, then player I and G needs to pay the cost F0 for such direct connection. But if players I and J, they belong to different groups, then what player I needs to pay? It is a difference between 2 numbers. The first is F1, which is definitely bigger than the cost F0. And the second, it is a fraction. This fraction somehow describes the fraction of player I's neighbor who come from the same group with player G. And under the second type, if players I and J belong to the same group, it is the cost F0. It is the same as the first cost function. And if players I and J, they are from the different groups, it is also a difference. And the first item is F1. But the second item, it is a maximum term among 2 fractions. The first is the same with the first one. It is somehow describe the fraction of player I's neighbor who come from the same group with player J. And the second term, they look very similar, but the second fraction describes somehow the proportion of player J's neighbors who come from the same group with player I. So from the 2 functions, we can easily get that under the first cost function, the cost for player I and J, it is not necessarily symmetric. So they may pay different values or different cost for the same link. But under the second cost function, both players, the cost that players I and J pays for the link IJ, it is the same. So the cost is symmetric. And here we have the assumption that F1 is bigger than this fraction for any group K. It means that for any possible link, we must have the positive cost for such link. Here there are some remarks about the cost function. So no matter under cost function 1 or 2, if players belong to the same group, they are not various types of players. Then player I has the same payment F0 under the 2 cost functions, and also player J, he needs to pay F0 for the link for connecting players from the same group. Well, if the 2 players I and J are from the different groups, the first cost function is not necessarily symmetric for the two players, but the second one is it must be symmetric for the two players. It is equal. And from the feature of the cost function, we have this kind of two effects on the cost. If one player is linking, like have more link to someone from another group. So if players I and J, they are from different groups. And now players I do not have the direct link with player J. If now he wants to have the link with such player J, it will has two effects on the cost of himself. On the one hand, it will decrease the average cost of all other like pre-existing links with such group. It means that if previously I have some links with players from the same group with player J, then if I newly add this link, it will decrease the average cost of the previous links with such group. On the other hand, it will increase the cost, or we see the average cost of existing links to other groups, groups which is not the group of player I and the player J. This is because that it increased the proportion of the second term. So, well, below I'd like to introduce the dynamic process of our work. Since in this dynamic process, we just assume that the network structure is fixed. So we see that the benefit of any player is not changed in the process. It is constant. It does not influence the dynamics process. So in this process, players only deviate from groups to groups. So only the partition structure is changed. So the utility maximization in the process is just equally or equivalent to the minimization of the total cost for each player. Now I'd like to introduce the dynamic process of this partition formation. So the process is discrete time and infinite horizon. And players start at stage 0 with an initially given partition, capital delta 0. And in this partition with M groups, there is no empty group. So there must be at least one player in each group. And at any subsequent stage, a random player is randomly chosen to make action. He can decide to deviate from the current group to any other existing one, or just stay in the current group. So for each player I, he has M possible actions at the stage he is chosen to make the action. Well, in these all the strategies, we concern the best reply strategy. So the best response strategy of player I is defined like this. If he can decrease the cost after deviation, he will choose the best choice to deviate to a certain group. But if he cannot decrease the cost, he will stay in the current group pi I. And of course, he has M actions at each stage he's chosen, and there may be very equal like actions for any player I. So the best response strategy may be not unique. And from now on, we assume that all the players play the best response strategies. So under the best response dynamics, given any initial partition structure, we see a partition structure is stable under the best response dynamics, or we just simply say it is a stable partition if there are two conditions and they are satisfied. The first is that there must exist a formation history The formation history is a history of partition structures, a series of partition structures. There is a formation history after which this partition structure emerges. It must appear. And then based on this partition structure, for any player I, if he is chosen to make action, he chooses to stay in the current one as the best reply. From now on, we give some results about the stable partitions. First, we assume that players are engaged in a very simple network, star network. And we mainly, investigate the tendency of the deviation in the best response process. How players deviate, how they deviate until the emergence of the stable partitions. The first result is that given any initial partition, we do not limit the number of groups in the initial partition, but it is a finite number m. And for any player I who is not the central player, he is selected at any stage, and he will definitely choose to deviate or stay in the group that player 1 belongs to. And under the second cost, this is the result for the first cost function. And when the second cost function is applied, given any initial partition, but with such inequality, it is the difference between f1 and f0, it must be bigger than such fraction. It is the fraction n minus 2 divided by n minus 1. So under such conditions, any player I who is not the central one, he is selected to make action. He must choose to deviate or stay in the group player 1 stays. So no matter under cost function 1 or under cost function 2, there is no condition anymore, but there is some condition. All the periphery players will follow player 1. And then there are some more like complicated results on the structure of stable partitions. So given any initial partition and the players are in the network of the star network, under the first cost function, if the gap of the difference or the gap is bigger or equal to this fraction, then there must be stable partition. And what the stable partition is satisfied? What is the condition for the stable partition? It is that all the players are in the same group. But on the other case, there is no stable partition. While under the second cost function, if the gap is very big, then there must be stable partition finally, and all the players belong to the same group in the stable partition. So there is one group containing all the players, and for all the other groups, they become empty in the stable partition. Well, if this gap is smaller than this boundary, there also exists stable partition, but the stable partition looks like this. All the periphery players in the star network, they stay in the same group, but the central player, he stays singly in one group. And if occasionally this gap is just equal to this boundary, then there are two cases. One is that all the players are in the same group, including the central one. The other case is that all the periphery players in one group and the central players is in one group. So this is the summary of these structures or stable partitions for the star network under the different cost functions. Well, to better feel the tendency of the deviation of the periphery players in the star network, let's see an example. It is more obvious. So there are 9 players with the initial partition of 4 groups. So the central player, player 1, is in the same group with one peripheral player, player 9. And players 2, 5, 6, 7, the 4 players are in one group. Player 4 is singly in one group, and the players 3 and 8, they are in another group. And we give the parameters the cost F0 and F1. And this is just the star network with the initial partition. And let us investigate this steeper partition under the two-cost function. Here, let's directly see the result. Under cost function 1, as the result we just summarize, this is such F1 and F0. The difference is 1 divided by 4. It is much smaller than the boundary. So we see that there is no stable partition. But here we see why there is no stable partition. We see that at stage 1, player 1 is selected to make action. And we can prove that player 1 chooses to stay in his current group 1. And at the second stage, here I forgot to note that in order to better feel the tendency of the peripheral players, we make an assumption on the order of players. We assume that player 1 is selected at the first stage, player 2 is selected at the second stage, and until player 9 is selected at the ninth stage. This is the first round. And at the second round, player 1 is selected again, and player 2 until player 9. So round and round. So we just make assumption on this example, but it will not influence our results on the stable partitions. So we can see that from stage 1 to stage 9, this is the first round. We see that the proportion of players in the group N1, it is gradually increases. And for the proportion of players in other groups, it gradually decreases. Why is it? Because all the periphery players, they chooses to deviate to the group player 1 belongs to. So after stage 9, after the first round, all players will be in the same group with player 1, just N1. And at the 10th stage, the second round starts. So player 1 is selected again to make the action. But what he will choose? He will choose to deviate to another group. So it is the fourth group. So player 1 do not want to stay in the same group with other peripheral players. He will deviate. He will escape. But after he escapes to the green group, the 11th stage, player 2 is selected again to make action. He always follow player 1. So he will deviate to the green group. And player 3, player 4 until player 9, they will deviate to the group player 1 stays in. But again, the third round starts, player 1 deviate or escape again. So under the first cost function, this process is a endless loop. So we can understand that under cost function 1, there is no stable partition. But under cost function 2, as we see from the result, there is stable partition. So at stage 1, when player 1 is selected to make the action, he chooses to stay in his current group, just group 1. But at the second stage, player 2 is selected to make the action. He will not follow player 1. He will deviate to the group with the maximum number of players. Here, this is the initial partition. So at the second stage, when player 2 is making an action, he will not deviate to the group player 1 stays in, but he deviate to the group that players 5, 6, 7 belongs to. So this is the group containing the maximum number of players. And at the third stage, player 3 also deviate to such group. Player 4 also. Players 5, 6, 7, they choose to stay, to not deviate. and the players 8 and 9, they choose to deviate. So after the first round, we see that all players, except the central player, they deviate to group 2. And after the first round ends, what is the situation? The situation is that the central player, he is singularly stays in the group N1, and all the periphery players are in the group N2. So this is just the stable partition, because under the cost function 2, player 1 only needs to pay f1 minus n minus 2 divided by n minus 1, such very small cost function. And because the symmetry of the cost function, all the periphery players will enjoy such small cost. So under cost function 2, there is a stable partition, and it looks like this. Well, we finish the results on star network. Then we put players on the complete network. So very simple structure. So we also get some very obviously different result under the two cost functions. But here we make an assumption that in the initial partition, there are only two non-empty groups, because if we do not have this limitation, the result, we cannot conclude a very general result. So given the initial partition and the network structure, the complete structure, we have the following statement. So under cost function 1, if players are equally distributed in the two groups, and player I1, a random player, is chosen at the stage 1 to make selection, then if under such inequality, the initial partition structure is just the stable one, but on the other case, the stable partition exists, but all the players will deviate to the group I1 stays in. All the players will deviate to the other group that player I1 does not belong to initially, and the group player 1 belongs to becomes empty. But if there are the players are not equally distributed in the initial partition and the boundary condition is satisfied, the initial partition is just the stable one. But if the gap is very larger than the boundary, then all the players will deviate to the bigger group. So the bigger group initially will include all the players, and the other group will become empty. Well, in the other case, so the gap is small, and we need to distinguish whether the total number of players is even or odd. If there is an even number of players, then in the stable partition, all the players are equally distributed. But if the number is odd, then they are almost balanced, but they cannot fully balanced because the number of players is odd. But the difference between the two groups is just one. So the difference between the two groups reaches the minimum. And under the second cost function, the situation is very complicated. It is like this, like players are equally distributed in the initial partition, but F1 and F1 minus F0, it is in an interval. The interval is determined by an even number x. Then what is the stable partition? It is that the group which contains player 1 initially, it has n minus x divided by 2 players, and the other group contains n plus x divided by 2 players. So it is not just extremely or balanced situation like the cost function 1. Well, in the other case, the group player I1 belongs to become empty. All the players will deviate to the other group. And for the case that players are not equally distributed initially, we have almost similar cases. Because the statement is in a mass, we look like this. So here, I'd like to introduce the results just by clear images. It is much more clear. So under the first cost function, and we have such condition, the gap is small, smaller than the boundary. Then under the first cost function here, initially there are some distance between the two groups, but gradually they will narrow the gap until there's no difference between the two groups. So there are equal number of players in the stable partition. But if the number of players is odd, it is not even, they also will narrow the number of players between the two groups until it reaches number 1. But under the second cost function, the same condition is satisfied. The cases are more complicated. They will just narrow or increase the gap between the two groups until x is reached. What is x? X is the number which determines, it's not determined, it is just the value that the gap f1 minus f0 is located in such interval, and such interval is determined by x. So in the stable partition, what is the difference between the two groups? The gap is what? It is determined by the difference between f1 and f0. Here just the example on complete network, which just illustrate this kind of cases. Under cost function 1, they must narrow the gap between the two groups until it becomes 0 because there are 40 players. And at the second cost function, they will narrow the gap, but they will reach a number not necessarily 0 or 1. In this example, it is just 4 because f0 and f1, the difference is located in such very specific interval. Then this is the final theoretical result on a balanced and complete bipartite network. So also given an initial partition and such symmetric network, we see that there always exists a stable partition under cost function 1 or under cost function 2. And under cost function 1, when the gap is small and initially the partition structure is like this, then the initial partition is just the stable one. So in each side, players are distributed equally into the two groups. It is just stable. Otherwise, if the initial partition is not like this, but there must be stable partition. But what is structure? It looks like this, that all players in side A belong to one group, and all the players in this part belong to another group. They must located in different groups. And if this boundary condition is satisfied and the initial partition is just the stable partition. And if the gap is it's larger than this boundary, then the initial one is the stable one if the initial one looks like this. Otherwise, all the players belong to the same group in the stable partition, like this. All the players, no matter from side A or side B, they belong to the same group for the stable partition. While under the cost function 2, the situation become complicated. And here I just remark one because it is obviously different under cost function 1. Here we see this. Here, as long as in one side, all the players belong to one group, it will ignore the structure of the other side. it must be stable. Here also, in this side, all the players belong to one group, and we ignore the structure of players in another side. It can be stable, or the stable partition look like this. And the previous result is about the initial partition with two groups. But for this kind of network, we conclude that under cost function 1 or 2, given any initial partition with m groups, there must exist stable partitions. And for any initial partition with m groups, we have such conclusions, but only under function 2, because we find that under function 1, all the three results do not hold under cost function 1. So under this condition, there exists stable partition. In the stable partition, all the players in both sets A and B belong to the same group. And when the gap is small, then in one set A or B contains only players from the same group, while there are no such kind of player from this group in the other set. While under the boundary condition, in at least one set A or B, all players belong to the same group, and there is no requirement on the other set in the structure. And the previous results are about the stable partition in the dynamic process. Here, just based on the results in the dynamic process, we have the stable partition in static setting. Actually, all these results are directly obtained from the dynamic process. Here, I will not repeat this because they just almost similar, but different concept. It is Nash stable. And just summarize like this. Well, here we apply our model to Zachary club model. So there are 34 agents in the club, but there is conflict between the administrator and the instructor, player 1 and player 34 in the club. So gradually, the 34 players are splitting into two clubs. And with the network structure, they communicate with each other, and the partition structure, we can see this figure. So all the white players follow player 1 in one club, and all the red players follow player 34 in another club. And we apply our model to this club example, and we get some results for this model. So we get that no matter under cost function 1 or 2, for this partition, like this, we have the following statement. It is that if we give the parameters f0 and f1, and this partition is stable under the two parameters, then if I increase the value f1, it will not disturb the stability of such group. And the second result is that if for player 1, based on such partition, if he cannot decrease his cost by deviation, then for any player I who stay in the same club with player 1, they all cannot decrease their cost by deviation. So if player 1 chooses not to deviate, all the remaining players will choose to stay in the current club, but not to deviate. And for player 34, who is the leader for another club, if he chooses to stay in the current partition or in the current club, not to deviate, then all the players in the same club with him will choose not to deviate, but to stay in the club with him, with player 34. And among all the 34 players, if the player 34 does not deviate, then all the players will not deviate. So under our cost function, if we want to examine the stability of the partition structure, we can just examine for player 34. If he does not want to deviate, then the partition structure is stable. And another conclusion is that under cost function 1 or 2, the stability of such partition structure is equivalent under the two cost functions. So the two cost function make no difference for the stability of such partition structure. And especially by proposition 1, we can better feel the leadership of player 1 and player 34. Because if they do not want to deviate, all the members of their club will choose not to deviate. Well, finally, we'd like to do some experiment because some people may wonder that you just get some result on very simple network, star network, complete network, very simple, regular, and symmetric ones. So we do some simulations just on random network. They are not simple, they are not symmetric. But here we do simulations only under cost function 1. But only with this we can feel that the result is very sensitive to the network structure. So we have 50 players. And in the simulations, we have two inputs. One is the network density. We have three possible values, 0.1, 0.5, and 0.9. Why we choose three values like this? Because for 50 players, the density of a star network is almost 0.04. And for the balanced and complete bipartite network, it is almost 0.51. And for the complete network, the density is 1. So we have the three similar values corresponding to the three networks. And the second input is the gap. So from the previous result, we see that the gap F1 minus F0, it is very important. It is just the boundary for different results. And we select the gap from the four values. And we need to note that on the previous result, the threshold, the theoretical threshold is almost this value. So the first three gaps are all smaller than the threshold, and only 1.1 is bigger than this threshold. So for each pair of values of density and the cost gap F1 minus F0, we run 500 simulations. And 500 simulations. And each run starts from 50 players, but 50 players are equally distributed in the two groups. So in each group, there are 25 players. And the process stops if the stable partition appears, or because it is possible that there is no stable partition. So we also stop the process when the simulation takes this number of stages. So after these stages of process, if no stable partition emerges, we will stop the process, and we regard it as no stable partition appears. There is no stable partition. And here are the results of the the simulation results. Here there are many figures. We will not see this, but just see the summary of all these results. Here, when the network density is 0.1, which is very sparse. The network is very sparse. And the value or the gap of the cost increases from 0.5 to 1.1. And let us observe the results. So in the first three cases, when the gap is less than the threshold value, it is possible that there is no stable partition. But when the gap cross the threshold reaches 1.1, there must be stable partition, 1% convergence. And this value just records the possible gap between the two groups in the stable partition. We see that it can be 0. It means that all players in one group and there is no player in the other group. And 12 means that there are players are not equally distributed, but there are more players in one group, there are less players in another group. And in these two cases, any even number of players, X, can be the gap between the two groups in the stable partition. Because we record 500 simulations and each number appears. 2, 4, even 14, 26, 30, all the even number appears. And when the density is 0.5 and 0.9, there must be stable partition. So all the ranks converges. And we see that when the gap is small, players are, extremely not not balanced in the two group. No, it's extremely balanced in the two group because the gap is 0. Players are equally distributed. And for 2, the gap is only 2 and the gap is only 4. But when the threshold, when the gap across the threshold, the case is quite different. It is only one result that the gap between the two groups is 50. It means that all players in one group and the other group becomes empty. And the same situation we can analyze for the density 0.9. So here, let us conclude for the simulation results. First is that the connectivity of the network really extends or shapes the result for the simple structure benchmark. So in the dense networks, we mean that the density is 0.5 and then 0.9. When the cost gap is smaller than the threshold, so the first 3 possible values, the convergence is universal. And we see here, it is universal, and the distribution of players among groups is very balanced. But how we see it is balanced or nearly balanced, because the gap between two groups is only 0, 2, and 4. And but if the distribution for density 0.9 is relatively close to the results for us for the complete network. Here, because for the complete network, there are 2 extreme cases. Like they can be equally distributed or all the players move to one big group and the other group is empty. So for the density 0.9, it is very close to our theoretical results for the complete network. The complete network, the density is just 1. And the second conclusion is that in the sparse networks, the density is 0.1. The outcomes are very diverse. There is a variety of outcomes. Here we can see from this table that they can balance, that they can almost balanced and they can or how to say extremely different between the two groups. Here just and there is a very special case for 0.7 here. We see that when the density is 0.1, the gap is 0.7. There, the convergence rate is less than 50. So more than 50 runs of the simulation, there is no stable partition. But for other cases, if we increase the gap, it is 99. Almostly there is stable partition. And when it becomes there 1.1, it is 100%. So this is the results for the sparse network with density 0.1. And finally, we observe that if the gap crosses the threshold, the structure or the features of the stable partition changes a lot. Here we can see this. From 0.9 to 1.1, from 0.9 to 0.1, from fully balanced or almostly balanced to extreme case. This is also the case. So that's all. Thank you for your attention.